Hi everyone, in this video we're going to see another application of integration. Specifically, we're going to see how the definite integral can be used to compute the work done by varying force. And of course the notion of work that's used here comes from the physics perspective. Let's start by defining force. So force, which we denoted by capital F, is a push or pull on an object. And the force is measured in newtons, uppercase N. And this is how the work is defined. By the way, we denote it by uppercase W. So the work is the measurement of force over some distance in meters in the direction of the force. So in short, from this definition, we can see that the work is defined by the force exercised over a certain distance. And the units of work are measured in joules, uppercase J. So here's that definition, but in a formula. So W equals F times D. Work equals force times distance. Or we'll also say displacement. And here's an important note. This equation defines work only when force is constant. So keep this in mind. So for the quick practice of what we just talked about and for the formula that we learned, let's look at this example. So here the question is, who has done the most work? As you can see in this picture, two people are applying same force, 500 newtons, to two different objects. So the person on the left is applying this force to an object that weighs 300 kilograms. And the person on the right applies that same force to a lighter object, only 100 kilograms. So what else do we see here? So we can also see that while the person on the left applies the force for 10 seconds, no movement of the object happens, so it stays on the same place. The person on the right applies force for less time, only 5 seconds, and is able to move this object 6 meters. I'm sure they both are sweating, but who has done the most work? The formula that we just learned will help us to answer this question. And I forgot to make a note that it's assumed that they applied constant force. So 500 newtons is the constant force that they applied. So to calculate work done by the first person, we have to take force that's being applied, well, it's 500 newtons, and multiply by the distance or displacement. And now it makes more sense why the word displacement is used, right? Well, since there is no movement of the first object, well, it means that displacement is 0. 500 times 0 is 0. So the work done by the person on the left is 0 joules. Even though the person is sweating, from the physics perspective, there is no work done. How about person on the right-hand side that's pushing a lighter object for less time? To calculate work done by the person on the right, we have to take force applied to the object. It's 500 newtons as well. But this time displacement is 6 meters. So I have to multiply that by 6. That means that the work done by the person on the right is 3,000 joules. And I added a couple errors just to clarify where I got the numbers. And once again, we use this formula when the force is constant. Now here's the question. What if the force is not constant? How do we compute the work? Well, let's see. On this picture, we have a particle that's being moved over the segment from A to B by applying certain force. But this time, force is not constant. Force is defined by function f. And look at that curve. See how it goes up and down, so it indicates that force increases and then decreases. But the bottom line, it's not constant. And the idea behind this graph is that if I pick any place or any point in A and B, let's say particle is over here, then I will be able to figure out what force is being applied to that particle at that moment. But the question is, how do we compute the work done by moving this particle from A to B if the force is constantly changing? Well, this is how we're going to think about it. We're going to subdivide the interval AB into n subintervals of the same width, and the length of each subinterval will be delta x. Let's say this is one of the subintervals, delta x. And for the purpose of doing this all in general, I'm going to say that this is ith subinterval. Now what I can do next, I can pick a point in that subinterval, let's say here, and I'll denote that point as x star sub I, because it comes from the ith interval. Well, can I find force being applied to the particle at that point? Yes, I can, and that is simply looking at the function value at that point. So force is f of x sub I star, force applied to that particle at that specific point. And since each subinterval is supposedly very small, I can use the force that I just found to approximate the work done by moving the particle over the subinterval. Remember, work is force times distance. So force is f of x sub I star times the distance. Well, the length of this subinterval is delta x. And that's where I wrote it. The work done in moving the particle over the ith subinterval is approximately f of x sub I star times delta x, force times distance. We're saying approximately because force that we're using here is specifically at that one point, but since the initial delta x is very small, again, we're using it to approximate the work. Now, can I do that trick for every interval? And the answer is yes, of course, why not? And then if I can find the approximate work done for each subinterval of the length delta x, what happens when I add those values up? Well, then I'm going to obtain approximation of the work done in moving the particle over the entire interval AB. So let me write this all down. So what I just said, that if I take f of x sub I star and multiply it by delta x, that's going to be approximation of the work done by moving the particle over the ith interval, right? Just that one interval. And I also said that if we add up the approximations of work done over all subintervals, well, then it's going to be the approximation of work done over the entire interval AB. Remember, for summation, we can use sigma sign in math, and to say that we're adding work done for all intervals, I have to say that I goes from 1 to n, from the first subinterval to the nth subinterval. But that is, again, approximation. If we have 10 subintervals, well, we do have approximation. If we make intervals smaller, let's say 50 subintervals, approximation is going to be better, right? If we take 50,000 subintervals, approximation is going to be even better. What would be the desired number of subintervals to have so it's no longer approximation, but the exact value describing the work done? Well, that number would be infinity. Agree? Then I'll say, well, let's take a limit where n approaches infinity. That will give us the exact value of the work. But do you recognize this limit? The limit of the Riemann sum? Most likely you do. And that is exactly the definition of the proper integral. Integral from a to b of the force function f of x, and then of course instead of delta x, I'm going to put dx. So that's going to be the way for us to compute the work done by a variable force in moving the object from A to B in the direction of the force. So let's try an example. It says when a particle is located at distance x meters from the origin, a force of cosine of pi x over 3 newtons acts on it. How much work is done in moving the particle from x equals 1 to x equals 1.5? So as you can see in this example, force is not constant, it's variable, right? So depending on the position of the particle, which is x, force will be more or less. This means that to find the work, we have to use this formula. Well, actually we have everything we need, right? We do have a force function, that's that cosine function. And we already have the limits of integration because it says here that particle is being moved from x equals 1 to x equals 1.5. So this means that to find the work, we're going to set up the integral with limits 1 and 1.5. The first function is cosine of pi x over 3. I'm going to write it this way. And then dx. To find the work, we just have to evaluate this integral. As I can see, it's not a basic cosine function because its argument, or what's inside that cosine, is not just x, it's pi x over 3. So I'll need to use the substitution rule. I'll do it on the side. So I will apply this rule with no limits involved. So it's just integral of cosine of pi x over 3 dx. So what I'll do, I'll denote everything that's inside the parentheses. I will call that u. So that means that u equals pi x over 3. And what is du? Du is pi over 3 dx. Let's figure out by what to substitute dx with. I will need to multiply the right hand side by 3 over pi and the left hand side by 3 over pi. This will cancel pi over 3 and 3 over pi on the right, and I see that dx equals 3 over pi du. Okay, so I will replace dx by 3 over pi du. Let me put this all together. So for this, I have integral of cosine of u times 3 over pi du. Well, 3 over pi is the constant, right? So I can place it in the front of the integral sign. So now I have 3 over pi integral cosine of u du. Okay, and I'm ready to integrate. So antiderivative of cosine of u is sine of u. So I'll get 3 over pi sine of u plus c. And I'll go back to the original variable of integration, which is x. So u I will replace by, well, whatever it equals to, so it's pi times x over 3 plus c. And now I'm ready to put that back into my definite integral. So I'm back here. I already integrated. Now I just have to evaluate the result. So I have 3 over pi sine of pi x over 3. That has to be evaluated at 1.5 and 1. Now, since I'm dealing with trigonometric function here, then it's going to be easier if I plug in not 1.5, but actually 3 over 2. I'm just going to rewrite it as a fraction. So that's what I'll use. That means I have 3 over pi. I'll still keep it outside. Then sine of, I write like that, pi over 3. That's this part. Times, well, x is 3 over 2. Like that. And then minus sine of pi over 3 times, and I'm plugging in 1, the lower limit of 1 times 1. Okay, so that's 3 over pi times, I can see that 3 and 3 I can cancel, so it's basically pi over 2. So what is sine of pi over 2? It's 1, and then minus, and here I have just pi over 3. So sine of pi over 3 is square root of 3 over 2. And I'll combine everything into one expression. Inside the brackets, I will subtract 1 and square root of 3 over 2. So for that, I need to put 1 over 1 and multiply the denominator and the numerator by 2. So that's 3 over pi times, so it's 2 minus square root of 3 in the numerator and then 2 in the denominator. And finally, as I multiply both fractions, in the denominator I'll have 2 pi, and in the numerator I must remember to distribute 3. So I'll have 6 minus 3 square root of 3. And this is the exact answer. This is 6 minus 3 square root of 3 over 2 pi joules. If I put that in the calculator, I will be able to obtain decimal approximation of this. Okay, so this is how you compute work if you deal with the varying force. So the force that changes, the force that's represented by a function. You need to know the displacement of the particle, so from where to where it's being displaced or moved. So use those as limits of integration, and you're integrating the force function.